Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the Scalable A/B testing platform, the system that powers trustworthy experimentation at companies like Google, Meta, Netflix, LinkedIn, and Spotify. We'll cover how to assign users to variance, collect and join exposure and outcome events, run statistical analyses, detect sample ratio mismatch, and guard user experience with guardrail metrics. Whether you're preparing for a senior engineering interview or building experimentation infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the Scalable A/B testing platform, the system that lets product teams, data scientists, and engineers run trustworthy experiments at scale. If you have ever wondered how Google, Meta, Netflix, LinkedIn, and Spotify decide which search ranking recommendation algorithm or user interface wins, the answer is a production-grade experimentation platform. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the statistical trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building experimentation infrastructure, let's get into it. Here is the core problem. A product manager wants to know whether a new recommendation model increases watch time on a streaming service. A growth team wants to test a new checkout flow. An ads team wants to compare two bidding strategies. Each experiment needs a random assignment of users into control and treatment groups, a consistent event pipeline, and a reliable statistical analysis. But at scale, this breaks in subtle ways. A bug in the assignment service causes one variant to receive twice as many users as the other, which is a sample ratio mismatch. A delayed event pipeline makes the treatment look worse because late conversions are missing. A feature flag rollout overlaps with the experiment, polluting the counterfactual. Mobile and web users are bucketed differently, breaking stratification. The platform must isolate true causal impact from these operational biases, and it must do so for thousands of concurrent experiments across hundreds of millions of users. Let's walk through the functional requirements. First, the platform must allow users to define experiments with clear hypotheses, primary metrics, secondary metrics, and guardrail metrics. Second, it must provide a robust randomization service that assigns users to stable, consistent variance based on deterministic hashing of a randomization unit, such as user ID, device ID, or session ID. Third, it must collect, validate, and join exposure and outcome events from web, mobile, backend, and data warehouse sources. Fourth, it must compute experiment results including lift, confidence intervals, p-values, and statistical power, while supporting multiple testing correction and sequential testing for early stopping. Fifth, it must detect and alert on sample ratio mismatch, guardrail metric violations, and underpowered experiments. Sixth, it must support a user interface for experiment configuration, status dashboards, and read-only reporting, plus integrations with feature flag systems and analytics tools. These capabilities make experimentation trustworthy and repeatable. Now the non-functional requirements. The platform must be highly available because assignment decisions happen on every critical user request, and an outage can corrupt experiments or break the product. Latency must be low, typically under a few milliseconds, for the randomization API call. The system must be horizontally scalable to support hundreds of millions of users and thousands of concurrent experiments. Consistency matters more than eventual consistency for variant assignment. A user must always see the same variant for the duration of an experiment. The analytics pipeline must be accurate and durable, because experiment decisions can move billions in revenue. The platform must respect privacy and compliance, including consent, differential privacy, and data retention policies. Finally, it must be extensible so data scientists can plug in custom metrics, counterfactual estimators, and stratification rules. Here is the high-level system architecture. On the left, the client surfaces including web, mobile, and backend services call the experimentation API gateway. The gateway routes assignment requests to a distributed randomization service backed by a cache and a configuration store. The assignment service reads experiment definitions, computes a hash-based bucket, and returns the variant. Simultaneously, exposure events are emitted to a Kafka ingestion layer. Outcome events such as conversions, clicks, and watch time are collected through the same telemetry pipeline or pulled from the data warehouse. A stream processor joins exposures and outcomes in near real time and writes to an experiment metrics store. A separate batch pipeline runs daily or hourly to compute aggregated statistics, sample ratio mismatch checks, and guardrail violations. The results are served by an analysis API to the experiment dashboard, alerting service, and external reporting tools. The key metrics to memorize cold. First, the primary metric or online evaluation criterion such as conversion rate, revenue per user, or watch time per user. Second, guardrail metrics such as page load latency, error rate, and unsubscribe rate, which protect the user experience. Third, sample ratio mismatch, measured as the chi-square statistic between expected and observed variant allocations. Fourth, statistical power, the probability that the experiment will detect a true effect of a given minimum detectable lift. Fifth, p-value and confidence interval for the observed lift, corrected for multiple comparisons and optional stopping. Sixth, counterfactual impact, often estimated as the difference between treatment outcomes and the predicted outcome for the same users under control. These metrics are what stakeholders and interviewers expect you to discuss first. Let's trace the end-to-end user journey. A data scientist at a streaming company wants to test whether a new ranking algorithm increases long-form watch time. She creates an experiment in the platform, defines the primary metric as watch time per user, adds a guardrail for error rate, and sets the randomization unit to user ID with 50-50 allocation. The configuration is pushed to the randomization service and feature flag system. When a user opens the app, the client calls the assignment service, which hashes the user ID and experiment key to return control or treatment. Exposure events are logged. The telemetry pipeline joins these with watch time events. After a few hours, the dashboard shows early guardrail checks. After a week, the sequential testing engine reports a statistically significant lift of 4% in watch time, no guardrail violations, and no sample ratio mismatch. The team ramps the winning variant to 100% and documents the learnings. The core models and algorithms. The randomization unit defines what is randomized: user ID, device ID, session ID, or page view. Hash bucketing maps a unit and experiment key to a stable bucket using a deterministic hash function, which avoids storing per user assignment state. Stratification ensures that buckets are balanced across important dimensions like country, device type, or user segment. Counterfactual estimation predicts what would have happened to treatment users under control, often using machine learning models or difference in differences to reduce variance. Sample ratio mismatch detection compares observed allocations to expected allocations using a chi-square test and alerts when the imbalance is significant. Sequential testing, such as group sequential tests or always valid p-values, allows peeking at results without inflating false positive rates. The alerting model prioritizes guardrail breaches and SRM violations above neutral metric movements. The key trade-off is statistical power versus runtime. Shorter experiments are faster but noisier and more prone to false negatives. Now the low-level design deep dive. The assignment service is a stateless, horizontally scalable API. It reads experiment definitions from a configuration store, applies a hash-based bucketing algorithm, and returns the variant. The service caches experiment metadata and supports emergency shutdown through a kill switch. The telemetry pipeline writes exposure and outcome events to Kafka, with schema validation and exactly once semantics for critical events. A stream processor joins events by randomization unit and emits per-user aggregates to an OLAP store. The batch statistics service runs scheduled jobs to compute lift, variance, confidence intervals, and SRM checks, using pre-aggregated data or bootstrapping for robustness. The metric store is optimized for time series and experiment-level queries. The dashboard API translates user requests into SQL or pre-computed rollups. Alerting rules are evaluated against the same metric store, and notifications are routed through email, Slack, or PagerDuty. For large experiments, the system uses incremental computation and pre-materialized summaries to keep refreshes fast. Key takeaways for your interview. First, an A/B testing platform is a trust system. Assignment, telemetry, and analysis must each be correct, because any bias undermines the counterfactual. Second, always define the randomization unit clearly and explain why it must be stable, consistent, and aligned with the analysis unit. Third, separate primary metrics from guardrail metrics and explain why guardrails are essential for safe experimentation. Fourth, sample ratio mismatch and sequential testing are the two most common operational and statistical pitfalls, so be ready to discuss detection and correction. Fifth, mention real platforms and practices, such as Google's overlapping experiment infrastructure, Meta's Planout and Experimentation Console, Netflix's sequential testing, and LinkedIn's stratification and counterfactual models. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the Scalable A/B testing platform. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the Scalable A/B testing platform. We covered the full picture from randomization services and hash bucketing, through telemetry pipelines, statistical engines, sequential testing, and the low-level design of the experiment definition and analysis pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.